Okay, Papa 2 friends. Today you're gonna continue learning about quadratic applications. We're doing the part 2 examples. So please download the Word document and open it up on your computer, or you can print it out. So you will need a calculator, so obviously have the graphing calculator ready, or you can use the computer software. So for part 2 of quadratic applications, you're gonna learn about projectile motion, which you should be familiar with if you're doing, taking physics. But basically, projectile motion are the questions where you throw an object up in the air and then it will have to come back down because of gravity. So for that, there's two equations you need to be familiar with. They're the same equations, just one equation tells you the height of an object if the units are feet. The other equation tells you the height of the object if the units are meters. So here, H stands for height. The T will stand for time. The V0, that stands for the initial velocity. So initial velocity. So how the speed of the object. And then the last one, the H0, that stands for the initial height. Like where did you throw the object from? Like from the ground or from a building? So H0 is initial height. So make sure you're familiar with the equations. And now we're going to start an example here, example 1. And these are the steps that you will be using in order to solve these. But let's just start reading example 1. A ball is thrown vertically upward from the top of a building. So that's going to be important. That's going to be our initial height because it is thrown from the top of the building with an initial velocity of 80 feet per second. So that's going to be our V0. Round to 3 decimal places when needed. Use interval notation if needed. Okay. So letter A, write a function for the height of the ball above the ground t seconds after it is thrown. So like I said, we're going to be using one of those projectile motion equations. And since the units here are feet, we're going to be using this equation that has the coefficient of -16 instead of the -4.9 because that's for meters. So we're going to say H equals -16 t squared plus V0. So the initial velocity was 80 t plus the initial height was 96 feet. So that's our equation. So step 1, write the equation. So we've done that. Next, letter B, you need to sketch the graph, label the axes, vertices, and intercepts. So we're on step 2. Use your calculator to graph that, find a good window, and you can find all the information that you need. So we're going to use our calculator. We're going to go to a graph, and we're going to graph -16. Now, don't put t squared. You're going to use x squared, because that's what the calculator uses for your function x. -16x squared plus 80x plus 96. Enter. And again, you have to find a good window. So the more you practice with the calculator, the better you'll be at finding a good window. It looks like in the x direction, this is perfect because I can see it go up and down. Or I can see the x direction is fine. The y direction, I need to change that y max. One way to change the y max is you can just go here, double click, and we don't want it to be 7. We want it to be probably at least 100. Okay, 100 was not big enough. 500? Okay, that was way too big. 300. That's fine. So that's one way to change it. You could also go to menu, window zoom, and zoom out like I showed you earlier, or my other favorite one is menu, window, zoom, and then if you go to window settings, I like that one. So remember the x direction was fine, -10 to +10, that was perfect. And the y direction, here you can change it if you wanted to make it -300 to +300. So you can change it that way. So now that I have my equation graphed, I do need to find the vertex and the intercept. So let's find the vertex. That's called the maximum. So I showed you before, menu, analyze graph, maximum. What happened? Control undo. Okay, menu, analyze graph, maximum. So take the cursor to the left of the vertex and to the right of the vertex, and that gives us our maximum. I also need to find the intercept, so I need to find this x-intercept. Menu, analyze graph, 0. So left of the 0 and right of the 0. The other 0 over here is negative. X can't be negative in terms of time, so I'm not going to worry about that one. But then there is one more intercept, which is the y-intercept. To find that y-intercept, there's different ways you can do. Just plug in x is 0 and into your equation here, plug in x is 0, and you can see that the y-intercept should be 96. I mean, it's in the equation. But you could also go to menu, trace graph, graph trace, and then you can put 0, and it gives you the y-intercept. But you can find it just by looking at the equation. This plus 96, that's the y-intercept. Okay, so now that you have everything on here, you need to graph it on your paper. So take all of that and let's graph it. So part B, sketch the graph. Make sure we label the axes. So down here, x-axis would be time, because that was x. The y-axis would be the height. And there you go. The y-axis would be the height. And now when I graph it, remember, okay, we only want to graph like the reasonable part of the graph. So basically, I'm only going to graph this part here because you can graph more if you want to using dashed lines. For example, like over here, the height of the ball can't be negative, so you can draw it if you wanted with a dashed line. Same thing over here, the time can't be negative and the height can't be negative, so you can draw it if you wanted with dashed lines like that, or only graph the reasonable part, which is just going to be this part there. And now label everything. The y-intercept was 0, 96. The vertex, which was the max, was 2.5, 196. The x-intercept was 6, 0. Okay, so everything's labeled and graphed there. So that was letter B. Letter C, state the reasonable domain and range and use interval notation for this situation. So the reasonable domain are the x values. So x is going to go from 0 to 6. It's possible for the time to be 0, so put a bracket. It's also possible for the time to be 6, so put a bracket. And your reasonable range is going to be from 0 to the maximum of 196. It's possible for the height of the ball to be 0, so put a bracket. And it's also possible for the height of the ball to be 196, so put a bracket, inclusive. Letter D, after how many seconds will the ball pass the top of the building on its way down? Okay, so this is one of these questions where you're going to have to graph it again, solve by graphing, but basically, the lights went off. So basically, you want to know after how many seconds will the ball pass the top of the building on its way down? So remember, this was the top of the building here at 96 feet. So we want to know when will the ball on its way down be at 96 feet again. So this is one of the ones where on your graph, you're going to go to the F2 and graph 96, because this is a y equals 96. So we can find out where those graphs intersect. So go to the graph, hit tab so that you can see F2, 96. Okay, there it is. And we want to find the second intersection. So on the way down, menu, analyze graph, intersection, and then again, menu, there you go, left, right, here we go. All right, so the ball is at 96 feet at the beginning when it was thrown from the top of the building at 0 seconds, and then it'll also be at 96 feet after 5 seconds. So that's what I can put for my answer, after 5 seconds. Or you can just put 5 seconds. Make sure you put units. Letter E, when will the ball be less than 110 feet above the ground? So same situation here, but this time instead of graphing a y equals 96, I want to be graphing a y equals 110, because I want to know when will the ball be less than 110 feet. So it's going to be a line here, y equals 110. So same thing, go to the graph, and this time let's graph y equals 110. hit tab, and then let's just go up and change the F2 from 96 to 110%. There we go. Oh, and it already gave me one of my intersections is already there, the 4.818. Okay, that's already there. We need to find, let me move this. We need to find the other intersection here. So menu, analyze graph, intersection. On the left of the intersection and on the right of it. There we go. Okay, we can see it there. So we're gonna write down those intersections and analyze the graph, but remember we need only 3 decimal places. So I showed you on the previous video how to just show 3 decimal places here instead of so many. We need to take that cursor over the number we want to change. Make sure the little hand is open, and this time press the minus sign because I don't want that many decimals. Minus sign. There you go. And same thing over here. Okay. That way doesn't want it. There you go. Okay. So at 0.182 seconds, the ball is at 110 feet. And then also at 4.818 seconds, the ball is at 110 feet. But we want to know when is it going to be less than that. So I guess before the 0.182, so before that, the ball is going to be less than 110 feet. And then after the 4.818, the ball is going to be less than 110 feet. So now we need to write that. It says to write it in interval notation, but first, let me just write it like set notation to see if it makes more sense. And then I'll change it to interval. So like I told you, based on the intersections, the ball is going to be less than 110 feet before the 0.182 seconds, because at 0.182 seconds, it is equal to 110 feet. Or it would also be less than 110 feet after the 4.818 seconds. But here's the problem with this. Other than the interval notation, here's this situation. I need you to give me your answers in terms of a reasonable domain. So remember that our domain here, you can't just leave x is less than 0.182 because then that means x could be all the way to negative infinity. And that's not right because our domain has to start at zero. So therefore, I'm going to put it has to be greater than or equal to 0. So less than 0.182, but greater than or equal to 0. Same thing over here, like x can't be forever greater than 4.8 because it can't go all the way to positive infinity. It needs to stop at the reasonable domain of 6. So here, like it needs to be greater than 4.8, but it needs to be, I guess, okay, less than 6, but we're going to fix that. Here's how we're going to fix that and write it in interval notation. So for my final answer, I'm going to put from 0, include the 0 because at x equals 0, the ball is definitely less than 110 feet. It's at 96 feet, so for sure is less than 110 feet. Comma, up to 0.182. Put a soft parentheses there because remember, like I said, at 0.182, the ball is equal to 110, and we want it to be less than 110. So put it like that. And then union, we need to go more than 4.8, so 4.818 up to the 6 because that's the maximum reasonable domain. And again, at the 4.818, put parentheses because that's when the ball is equal to 110, but you want it less than. And then at the 6, you can put a bracket because at x equals 6, the ball is at the ground, which is definitely less than 110 feet. So that would be letter E. Make sure you practice those. So let's leave it in interval notation because that's what it wants. So we can cross that out. And finally, number 1, letter F. How far had the ball traveled when it reached its highest point? So be careful with the question there. At the highest point, the ball is at 196 feet, but 196 feet, but that's not the answer. That's the highest height, 196 feet. However, the ball started at 96 feet. So here, I need to do 196 minus 96. So the ball had only really traveled 100 feet when it reached its highest point. So that's how you do an example with projectile motion. And make sure you're just familiar with that practice for the homework tonight. Example 2, I'm not going to work it all the way out. I'm just going to set it up where it says, when a rocket was launched vertically upward, it was released 12 meters above the ground. That's going to be our initial height, with an initial velocity of 225 meters per second. So it's going to be our initial velocity. Write a function. Okay, so it's going to be h equals. So this one, because the units are the meters per second, you should be using the negative 4.9 coefficient. So when you write your equation, it will be h equals negative 4.9 t squared plus the initial velocity of 225t plus the initial height of 12. And then basically you would put that in the calculator and then answer a bunch of questions. But for now, that's all it wants you to do. And that's how you do projectile motion. Okay, so now the second part of today's quadratic applications is called quadratic regression. You should be familiar with quadratic regression, or I guess at least linear regression, and it's the same process. So quadratic regression. To calculate the regression, we're going to input our data into a spreadsheet. Okay, so these are the steps, a bunch of stuff. Okay, let's just jump straight to the example. So example 3. Below is the number of feet required to stop and the distance at which the car is traveling prior to applying the brakes. So I have speed and the stopping distance. So depending on how fast you're going, so it's going to be x, or independent variable, that's going to determine your stopping distance. So it's going to be y. So letter A, write a quadratic regression equation for the data. So we need to do a quadratic regression. So I guess these are the steps. Step 1, input the data into a spreadsheet. Label the independent variable column X and the dependent variable column Y. So get your calculators ready. And we need to input a spreadsheet. So if you go home, I'm just going to click on this Excel looking document. That's the spreadsheet. And I'm going to input that data. So 10. Oops. And input the Y. Okay, and step 1 says make sure you labeled your column. So over here in column A, where it says A there, I'm going to call that X. It makes it easier if you just label your columns. Column B is going to be the Y variable. Call it Y. Okay, now make sure you bring your cursor over here in the actual spreadsheet. Don't leave your cursor up there in the columns or it's not going to work. So from here, anywhere here. Step 2. I'm just reading the notes. So these are the notes. Make sure you go through them. Step 2, press menu, statistics, stat calculations, and find the quadratic regression. So menu, statistics, stat calculations, find the quadratic regression. Okay. Step 3 says for the X list, we called it X. We call it X. Hit tab. For the Y list, we called it Y. Y, and leave everything else as is. Press OK. Or just press enter. So there we go. It's going to give you a quadratic regression in terms of ax squared plus bx plus c. So that's what we're going to copy. A is 0.05, b is 1, and c is 0. So my quadratic regression here, we're just gonna call it y equals 0.05 x squared plus 1x plus 0, because c was 0, b was 1, and a was 0.05. So that's letter A. Letter B says predict the speed when the stopping distance is 500 feet. So I need you to predict an x value when the y value is 500 feet. What is x? Well, I'm just going to show you. I'm just going to read the examples or the steps here. To make exact predictions, to predict a y value given an x value. Nope, we're going to do this one. To predict the x value given a y value, we need to go from the graph, add a second equation. Okay, so Okay, first of all, we're gonna have to add a graph in order for you to make any of the predictions. So to add a graph, what we need to do is from the spreadsheet that we were just at, we're gonna press Doc, Insert Graphs. Then you have to press up so that you can see your equation and press Enter to zoom in. So right here, press Enter. All right, so let's try this. Okay. So from my spreadsheet, I'm going to go where it says to add the graph, press Doc, Insert, Graph. Okay, it looks like there's nothing there, but it says press the up arrow to see your equation stored in F1. So there it is. Press the up arrow. There's your equation. It's been stored. Now you need to press Enter for it to graph. If not, it won't graph. Press Enter for it to graph. That looks good. Okay, now we need to find a good window. So whatever you want to do to find a window, I'm going to go to try Menu, Window, just zoom out. Okay, I mean, that's good enough. Escape. So well, that's not good enough, but I'll fix it. Okay, so there's my window. And now that I have my graph, I'm ready to make my predictions. So I guess I'm still on letter B. Predict the speed when the distance is 500. So like I told you, 500 feet is a y value, so we need to type y equals 500 and find the intersection. So if you press tab, y equals 500, press enter, and obviously we're going to have to change the window, zoom out some more, or let me just change this to 1,000. Oh, but then I need to change my x max to 500. Okay, so that was a little too much, but that's enough. Don't do that. Control, undo. Okay, find yourself a good window that works, and so that you can see your intersection. Remember, you could also go to Menu, Window Settings, and try to fix this. I don't know. Let's see, -500, 500, and then let me just do -1,000 to 1,000. I was just playing with it. There you go. Okay, and I'm only interested in the positive intersection because x can't be a negative speed. So I'm just going to be over here in the positive intersection. Menu, Analyze Graph, Intersection. Lower bound. Click. Click. There you go. So if the stopping distance is 500 feet, the speed is 90.4988. And remember, we only want to round to 3 decimal places. That was the wrong way. Minus. There you go. So x would be 90.499 miles per hour, because I guess that's what the units are for speed. So you copy it down. So over here, if the y was 500, x was 90.499 miles per hour. So that's my answer for that. And finally, letter C. You are traveling at 65 miles per hour, so that's an x value, and you see a deer standing in the road at 280 feet in front of you. As soon as you see the deer, you hit the brakes. Will you stop in time or hit the deer? Well, hopefully we'll stop in time. So, so this is kind of asking you, what I would do is, given that x is 65 miles per hour, let's find the y value to see what's the stopping distance, and hopefully it's less than that 280 so we don't hit the deer. So in order to do that, I'm going to go over here where it says to predict the y value given an x value. What you can do from your graph, go to Menu, Trace, Graph Trace, and type in that x value that you want. So from my graph, I'm going to go to Menu, Trace, Graph Trace, and I want x to be 65, so type in 65, enter. Enter one more time. I guess press enter twice so that you can see the actual point. But it says that if x is 65, the stopping distance would be 276.25. So I guess, let me write it down. So if x is 65 miles per hour, stopping distance, I'm explaining, stopping distance is 276.25 feet. So we will stop on time, barely. So we did stop on time, like right in front of the deer before we hit him. And now that's how you do some quadratic regressions. Please use these notes to practice your homework. Good luck.